When a physical beam is subjected to a load, it deflects as a single, continuous curve, rather than bending in fragmented pieces. Previous mathematical derivations have focused entirely on an isolated single beam element, generating equations that describe how a solitary segment behaves in a vacuum. Because real engineering structures consist of interconnected spans, the single element model cannot account for the continuity found in real-world analysis. To bridge the gap between a single piece and a whole structure, we require assembly, the mathematical process of translating isolated element equations into a single, unified global system. We can observe this algorithm in action through a simple case study, a structure composed of exactly two connected elements. These elements share identical physical properties, including the modulus of elasticity, the second moment of area, and the length. Maintaining uniform material and geometric properties across the structure eliminates algebraic noise and exposes the pure mathematical logic of structural connectivity. This schematic represents our case study, a single continuous beam split into two discrete elements, connected across three distinct nodes. Before calculating forces, we must define the degrees of freedom, the independent ways a node moves under stress. At node 1, the beam can deflect laterally, denoted as V, and it can rotate, creating a slope denoted as theta. Every node shares these two parameters. Mapping this establishes 6 sequential degrees of freedom for the entire structure. We then define the element boundaries. Element 1 exclusively connects node 1 and node 2. Element 2 exclusively connects node 2 and node 3. With 3 physical nodes each possessing 2 degrees of freedom, the final global mathematical model must account for a total of 6 interrelated variables. Generating a global model requires constructing an entirely new matrix sized to fit the total system degrees of freedom. This grid represents the total system. To account for every variable, we initialize an empty 6x6 global matrix, where each row and column corresponds to one of the 6 degrees of freedom. We fill this matrix by pulling from the local stiffness matrix of element 1. This 4x4 matrix dictates the behavior specifically between the first 2 nodes. Because it connects node 1 and node 2, element 1 influences only the first 4 global degrees of freedom. Through an algorithmic transfer, the local stiffness properties of element 1 are mapped into the upper left quadrant of the global matrix. At this stage, the global matrix describes the stiffness of the first segment, but it models a structure where the second segment does not exist. We now pivot to element 2, which governs the behavior between node 2 and node 3. Because the physical properties are identical to the first segment, the local 4x4 stiffness matrix for element 2 contains the exact same terms. However, it is assigned to global degrees of freedom 3, 4, 5, and 6. We map this second matrix into its corresponding lower right coordinates within the global array. This mapping creates an intersection. In the center of the global framework, the properties of both elements now occupy the same coordinates. This brings us to the principle of superposition, which requires the additive accumulation of structural properties at shared physical nodes. This central 2x2 overlap zone serves as the mathematical joint for node 2, dictating how forces and stiffness pass between the distinct elements. Overlapping matrix terms must be algebraically summed to determine the final stiffness of the joint. Focusing on row 3, column 3, we see the terms for lateral deflection. The blue term from the first element and the orange term from the second add together to form a value of 24. This value doubles because both elements provide equal resistance to vertical deflection at their shared connection, increasing the total rigidity. We see a different result in the off-diagonal terms, which govern the interaction between deflection and slope. Summing the positive 6L from element 1 and the negative 6L from element 2 results in a value of absolute 0. Physically, the identical but mirrored bending resistance from both sides of the node perfectly cancel each other out in the global system. Assembly transforms raw data organization into a direct computation of structural continuity. The overlap calculates where adjacent properties reinforce the beam or neutralize one another. Stiffness represents one side of the structural equilibrium equation. The other side governs the forces acting upon the system. We establish a global force array as a 6x1 column vector to match our 6 degrees of freedom. The forces acting on individual elements must also be mapped to these global coordinates. Loads from element 1 map into the top of the vector, while loads from element 2 map into the bottom. Following the rule of superposition, the force terms mapping to the shared joint at node 2 are algebraically summed. This accumulation ensures that any load applied at a joint distributes its effect across both adjacent structural elements. This completes the structural equation, KD equals F, where the fully populated global stiffness matrix is set against the global force vector. The final array contains distinct zones, independent terms on the edges, and centralized zones defined by joint mechanics. The merger of these isolated arrays creates a single, indivisible mathematical model that mirrors the behavior of a physical structure. This assembly algorithm, mapping local variables to global arrays and applying superposition, scales to any engineering problem, from a two-element beam to a skyscraper simulation. However, this global matrix cannot yet be algebraically inverted to solve for deflections. Mathematically, this is because the model lacks anchor points. We have defined the structure, but we haven't bolted it to the ground. Without constraints, the system undergoes rigid body motion. Any applied force will simply accelerate the whole structure indefinitely through space. To transform this into a solvable engineering problem, the matrix must be artificially constrained. Applying these boundary conditions is the final step required to lock specific nodes in place and calculate the true displacements of the structure.